Hello, my name is Kucherenko. I'm a research scientist at SEED at Electronic Arts, and today I'm going to share with you the work I've done during my PhD at KTH, together with Rajmund, Nagy, Michael Neff, Hedvig, Kjellström, and Gustav, Henter. And the motivation from this work comes from the importance of body language in human communication. As you probably know, body language plays a crucial role in our human-to-human communication. And hence, artificial agents should also use body language. They should not be static like a statue. Instead, they should use body movements to enhance their communication. They should use gestures when they speak. And it's an active research area to map human gestures onto the artificial agents. And data-driven models can already generate realistically looking beat gestures for virtual agents. But it is still an outstanding question whether they could consistently generate gestures that have meaning. We present promising results that indicate that the answer might be yes. There has been two main paradigms for gesture generation: rule-based and data-driven. Rule-based systems were usually made by experts based on theories and observations on human gesticulation. The rules are typically hard-coded, and hence those models are not flexible. On the other hand, since those rules are designed with having communicative intent in mind, they usually can produce gestures which convey meaning. And data-driven models instead learn such a mapping from the data using machine learning, usually by applying deep neural network, and they can generally generate unconstrained and continuous motion. And here you can see the development of the gesture generation field over time. The initial systems were rule-based, and they were driven by intent, and that's why they had fairly high communicative efficacy, but they were still very rigid and not really natural, as you can see on this image, where he's probably saying, "Keep walking forward." And more recent systems, which are based on machine learning, often look much more natural and fairly human-like, but typically do not communicate as much, as you can see on this example.
Like they may not necessarily be good for each other in the long run, but it's all about kind of like, it's just about being a stupid.
And now moving forward, the pursuit of natural and meaningful gestures is a hot trend in data-driven gesture generation. Unfortunately, the actual results do not necessarily live up to the claims, and convincingly meaningful gestures have not been demonstrated yet, and that's what we strive towards. We propose to combine the two paradigms of rule-based gesture generation and data-driven gesture generation. And we suggest to have a system that would first use deep neural network to predict semantic properties of the motion, which is akin to the motion specification of a rule-based system, and then add those properties as an extra conditioning to the data-driven gesture generation model. Therefore, the resulting motion can in theory be both meaningful and natural looking. And this paper is focusing on that top component of the system. We investigate the feasibility of such a mapping. And the central question is, given the data we have today, is it possible to predict semantic properties of gestures based on speech only? And if yes, then it means that agents which are generating meaningful gestures using data-driven methods are within our reach, and we have already proposed a framework for that. And if not, that probably means that field is not fully ready for such a pursuit. And this would suggest that a lot of recent work in this direction, which has struggled to convincingly demonstrate meaningful gestures, might have been simply premature. Let me show you the task setup. So first, we cut the audio and text sequences in temporal windows. Then we fuse them together using the machine learning model to predict a set of probabilities for gesture existence and for gesture properties. So we first predict if there should be a gesture at this moment in time, and then we predict what kind of gesture would be the most appropriate. And dataset we use for this task is a Sega dataset, which have been recorded in Bielefeld in Germany, and was kindly provided to us by Stefan Kopp and the team in Bielefeld, which we are very grateful for. And in this dataset, they had very interesting recording setup. First, the participants were taken on the bus tour in virtual reality, as you can see on the picture on the top, where they would all follow exactly the same route. And then they would have to describe this route to another participant, as you can see in the picture on the bottom. And in this setup, they had a lot of gestures conveying meaning, so-called representational gestures. And because the dataset was collected in Germany, and naturally the language was German, they had 25 subject recordings, summing up to 4 hours of data, and speech and motion were in the video MP4 format. We also had word-aligned transcriptions and gesture property annotations. And to the best of our knowledge, this is the largest dataset with this kind of detailed gesture property annotations. And talking about gesture property annotations, let me illustrate them using Elan interface. So on the top left corner you can see the video, and on the bottom you can see rows of temporal annotation. And I'm going to highlight those gesture properties which we considered in this work. A gesture category, which can be either didactic, beat, iconic, and discourse. You can see that most of them were iconic. A gesture semantics, which means which information is being put into gesture. Could be amount, shape, direction, or size. And gesture phase, which could be either pre-hold, post-hold, stroke, retraction, or preparation. And note that the classes are heavily imbalanced. And with this information, we could potentially predict, as an example, that at a particular time there should be a stroke for an iconic gesture that conveys size information. Now, when it comes to comparing our system with some baselines, there was no easy way to do that. First of all, it's a very difficult task, even for humans, to predict properties of a gesture given speech only. And there was no prior work that was trying such a detailed, fine-grained annotation, prediction of gesture properties. So we cannot really compare to previous work. And that's why we compare to simple bottom line systems. We had two systems always predicting the same value, either always 0 or always 1. We had one system uniformly making a random sample from all the possible values, and we had informed random system which randomly sampled according to class frequencies in the dataset. And the goal was to perform better than all of those bottom lines. And when that happens, we say that we perform better than chance. And the dataset we've been working on is highly imbalanced. And we looked in different ways to evaluate this binary classification problem. Accuracy, precision, recall, and F1 scores. And we have seen that very naive baselines or bottom lines, such as always 0 and always 1, can have very high scores in some of those metrics, which is unacceptable. And hence, we've selected a macro F1 score as our main metric, which is the average of F1 score for presence and absence of the label, and it's fairly stable to the class imbalance issue. Here you can see the results for gesture presence prediction, and the bottom lines had F1 score of below or around 50%, and our models on the left, depending on the modality used, were all performing much better and around 70% macro F1 score, so we can see that we could predict gesture presence better than chance. Here you can see results for gesture category labels, and you could note that we could predict didactic, iconic, and discourse labels better than chance. Here's the results for semantic labels, where we performed better than random for all of them. And the semantic properties are the most important for our end goal. And so it's really encouraging that we could have good performance here. Here you can see gesture phase, which has very different numbers because here we report F1 score for presence instead of macro F1 score. And that's because gesture phases are mutually exclusive. Only one can be active at a time, and hence we cannot consider them as independent. but we still have either comparable or better performance than random. So what can we learn from this work? Well, we've shown that it's in fact possible to predict multiple gesture properties from speech. And we have much more details in the paper, and there you can find that for predicting gesture category and semantics, text had the most important information. And for predicting gesture phase, it was prosodic audio features which were the most useful. And we believe that it's a big step for the field, because even a small fraction of meaningful gestures can make a lot of difference in how agents are perceived. Of course, our work had some limitations. We only considered one specific dataset, we only considered a few model architectures, and annotation gesture properties can be quite expensive. The conclusion of this work is, when learning something new, we should not forget the old. And when building new gesture intonation models, we should probably take inspiration from the old models. And we have validated that it's in fact possible to predict those semantic properties from speech only, and in the future work, we should integrate it in a complete system. And we follow open science principle, motions, dataset extension, and system implementation. All will be available on the project website. So you can head there for more information.